Now, in this video, we're going to see some of the consequences of Baer theorem. So the first one is called the uniform boundedness principle, also known as the Banach theorem, and it tells us the following. If we have a family of bounded linear maps between two Banach spaces, and this family is bounded pointwise, so for every x, it's bounded, possibly in a way that depends on x, but uniformly in n, then it's actually uniformly bounded in the operator norm. So the constant can be chosen independent of x. I've written it in that way to emphasize the fact that it's an automatic uniformity in x of this bounds on the family of operator. So we're going to prove this theorem first, and then we'll derive a corollary of it that tells us that if I have a set in a Banach space, I can test set B, I can test whether or not that set is bounded. That is to say that, the supremum of the norms of element of that set is finite by only testing the elements of that set against linear functionals, right? So this is what you might call weakly bounded. So it's bounded when you project it using down to R using linear functional, and this is equivalent to being strongly bounded, so being bounded in the norm topology of your Banach space. Right, so let's prove the Banach theorem and its corollary for weak implied strong boundedness of sets in Banach spaces. So we have Tn's that are bounded linear operators between x and y, and they are such that the supremum over n of the Tn of x is finite for all x in x. Okay, so I'm going to define for every capital N, or maybe let's call it M in N, the set xm, which is going to be a subset of x, which is going to be the set of all those x, such that for every n in n, Tn of x is smaller than capital M. Right, now, what does my assumption tell me? My assumption tells me that the union of all the xm is equal to x. Right, because the supremum is finite, so it's smaller than some capital M for some m. Now, because my Tn are all continuous, I also have that xm is closed. Right, moreover, xm is closed. If you take a sequence of x such that the supremum of Tn of xj is smaller than m and xj has a limit, then the limit will satisfy the same bound. So, okay, so I have closed sets which union is the entire space. So if the union is the entire space, it's certainly not small. So in particular, its interior is not empty. So we have that the interior of the union of the xm is non-empty. And so by the contrapositive of Baer theorem, right, if all of the xm's had an empty interior, then the union will have an empty interior. So the union does not have an empty interior. In fact, it is the whole space. So at least one of the xm, there has to exist an m such that xm has a non-empty interior. Okay, has non-empty interior, so I can find a ball inside it. So there exists an m, and there exists a x0 in xm, and there exists a radius, let's call it r0, positive, such that the entire ball, x0, r0, is included in the interior of xm. Right, now what does that tell me? That tells me that there exists an m such that, and there exists an x0, I suppose. Is that what I want to say? No, I'm just going to say it like this. There exists an m such that for every z in the unit ball, and for every n in n, Tn of x0 plus r0, say, over 2 times z, that describes an element of the ball centered at x0 with radius r0, is smaller than m. Okay, but now that I have that, that means that for every z in B of 0, 1, what can I say, and for every n in n, what can I say about Tn of z? Well, I can rewrite Tn of z as Tn of r naught over 2 times 2 over r naught of z. So this is certainly equal to 2 over r naught Tn of r naught over 2 of z. And now by triangle inequality, this has to be smaller than 2 over r naught times m plus Tn of x naught, right? But x naught was also chosen inside xm, so Tn of x naught is also smaller than m. So this entire thing is smaller than 4m divided by r naught. And that's true for every z in B of 0, 1. So then by linearity, what have we got? We've got that the supremum over n of the norm of Tn has to be smaller than 4m over r naught, which concludes the proof of the uniform boundedness principle. Okay, so now we turn to the proof of the corollary that tells us that weak boundedness and strong boundedness of sets in Banach spaces is the same thing. So we're going to prove that. We have a set B in a Banach space, and we're going to prove that it is bounded if and only if the projections, the one-dimensional projection x star x for x running over B are bounded for all x star in the dual, right? So on the right hand side I would call it weak boundedness, on the left hand side strong boundedness, boundedness in the norm topology of x, and the two things are equivalent. Now in the proof, well, one direction is obvious, right? If you're strongly bounded, then you're weakly bounded because x star x is always going to be smaller than the norm of x star times the norm of x. So this is smaller than the norm of x star times the supremum over all x in B of the norm of x. So if B is bounded, then the set of all x star x in a product, not in a product, duality product x star x for x in B are also bounded. Now the other direction that requires our uniform boundedness principle, it's the weak implies strong. And how do we do this? So we define a family of operators. So for every B in B, we define TB to be a map from x star to R. Actually, let's just say it straight away. It's going to be a bounded linear map from x star to R. So really an element of x star star, the bidual of the Banach space, defined by TB of x star equal the duality product of x star with B. Right, so we define these families of map, and now what have we got by assumption? So by assumption, we have that for every B in B, there exists, for every x star in capital X star, there exists a constant, possibly depending on that x star, such that TB of x star, if I take the supremum of that over all B in B, this is in absolute value smaller than C x star. Right, so what is that telling me? It's telling me that I have a uniformly bounded family of linear operator in the pointwise topology of linear operators between x star and R. And now I want to apply the uniform boundedness principle. Now, you might notice at this stage that I've only stated the uniform boundedness principle for countable families, and I'm applying it right now for a family that's uncountable. But really, the proof of the uniform boundedness principle that we just saw has nothing to do with the family itself, Tn being countable. So it works just as well for uncountable family. I just wrote it with n in n. So by uniform boundedness principle, what have we got? we've got that there exists a C that is common to all of the X stars, such that for all X star and X star, the supremum of a B in B of TB of X star, or let's put it this way, the supremum B of a B of the norm of TB as a bounded linear map from X star to R, so as an element of the bidual, is smaller than C. Right? That's what the uniform boundedness principle is giving us. Now remember that Unbalanced theorem gives us the existence of norming functional. So Unbalanced theorem tells us that for every B in B, there exists a B star in X star that has norm 1 and is such that the norm of B is the duality product of B star with B, which by the way is equal to TB applies to B star. But if it's TB applies to B star and B star has norm 1, that means for every B in B, the norm of B is smaller than the norm of TB, which is smaller than C, and C was independent of B. So there exists a C independent of B, such that for all B in B, the norm of B is smaller than C. That's exactly saying that the set capital B is bounded. And that concludes the proof.